I've shown the ANSYS results of that superposition. And then I've also calculated it by hand. So I'll go to the hand calc first. So I've added load case 1 plus load case 2, and this is the resultant stress tensor. And again, I've gone through and I've calculated the principal stresses. So the max principal is 1221.1 and minus 39.7. And I've calculated the normal stress in the x direction to be 391.5 and the normal stress to be 79.9 in the y direction. And the shear stress is 598.1. And if we look at the model, we see that the the ANSYS results, the maximum principal stress is 1221.1, which agrees well with the hand calc. And the minimum principal stress is minus 39.7, and that's what we get from the hand calc. And if we look at the normal stress in the y direction in the global coordinate system, we get 789.92, and that agrees with our hand calc. And again, z is 0, and in the x direction, we get 391.5, and again, that agrees. And now I've also calculated the angle, again, that you'd have to rotate the original axis or the original coordinate system into to align with the principal stresses. And I guess to really drive the point home, what I've done is I've gone in and I've created a coordinate system that is rotated based on the angle that we calculated. So we calculated a rotation angle of minus 35.78. And I've created a new coordinate system. I've called it eigenvectors and rotated it by that angle relative to the global coordinate system for that at that node location. And we can go in and we can look at if we look at the normal stress in the y direction, it should equal one of the principal stresses. So if I go in here and click insert stress normal, and we'll pick the y-axis. And the coordinate system that we'll use is our eigenvectors. And we'll do it for that node in the middle. And we'll click solve. And yeah, we get the maximum principal stress here. You see that it's 1221.1. And that makes sense. But I think it helps to kind of see if you do this out that the principal stress is acting in this direction, and you can create a coordinate system that aligns with that principal stress. And I guess for completeness, we'll go through and we'll do the x direction stress in that local coordinate system. Click solve. And there we get minus 39.675, which agrees with our minimum principal stress. And again, if we look at the vector principal stress result, we see that, well, at least they've normalized it they've normalized the vectors based on the stress results, so it's hard to see the vector that aligns with the minimum principal. But if we look at that arrow, it looks pretty, I mean, it should be exactly the same as our eigenvectors. Now we can look at the shear stress in that coordinate system. We will look at shear. And in our eigencoordinate system, click solve. And it's pretty close to 0, which we would expect. So that tau xy, that shear stress xy in this coordinate system is 0. And again, just because the shear stress result you get in that coordinate system is 0 does not mean that the shear stress on the part is not 0. So if we look at the part, we'll see that there is a shear stress in the part. And we can look at the maximum shear stress, which is just a function of the max and minimal principal stresses. Maximum shear. And you can see here, if you click on a principal stress option or the maximum shear stress option, you can't look at it in a coordinate system because it's invariant of the coordinate system. So if we click solve, it'll show you where your maximum shear stress is. And again, the principal stresses, I'll add the principal stress in here for the whole part. And again, you can't look at it in a coordinate system because it's invariant.